Picture a single moment in the vast emptiness of space where darkness stretches endlessly until suddenly, a flash erupts with more energy than a million suns. In less than a second, it unleashes power so immense it could outshine entire galaxies. This isn't science fiction, it's real. These are the universe's most violent explosions, cosmic events so colossal they defy imagination. And today, we're diving deep into 30 astonishing facts about these breathtaking phenomena, events so energetic they rewrite the laws of physics as we know them. What causes these titanic bursts of energy? How do they shape the cosmos around us? The answers are more incredible than you might think. From hyperactive supernovas to mysterious gamma-ray bursts that flicker like cosmic fireflies, these explosions aren't just destructive, they're the universe's way of creating, scattering the very elements that make up stars, planets, and even us. Think about it, the iron in your blood, the calcium in your bones. They were forged in the heart of these apocalyptic blasts billions of years ago. You are quite literally made of stardust shaped by the most violent events imaginable. But the story doesn't end there. Some of these explosions are so powerful their light travels across billions of light years, carrying secrets about the birth and death of the universe itself. Others vanish in the blink of an eye, leaving behind only riddles for scientists to unravel. And the most mind-bending part, we've only just begun to scratch the surface of understanding them. So get ready, because over the next few minutes, we'll explore cosmic detonations that challenge everything we know, reveal how black holes are born from chaos, and even uncover how a single burst of energy could hold clues to the fate of the entire cosmos. Strap in, the universe is about to show you its most spectacular fireworks, and trust me, you won't want to look away. One of the most staggering phenomena in the cosmos is the gamma-ray burst, an explosion so bright it could outshine a billion galaxies combined. In just a few seconds, a single GRB unleashes more energy than our Sun will emit over its entire 10 billion-year lifespan. These aren't just cosmic fireworks, they're the universe's ultimate powerhouses, capable of lighting up the darkest corners of space with blinding intensity. The story of their discovery is almost as dramatic as the bursts themselves. Back in the late 1960s, American military satellites designed to detect nuclear tests in space picked up something unexpected: brief, intense flashes of gamma rays that didn't come from Earth. Scientists were baffled. These weren't secret weapons or failed experiments. They were cosmic in origin, arriving from deep space at random intervals. For decades, their true nature remained a puzzle. Were they collisions of neutron stars, the screams of dying hypergiant stars, or something even more exotic? Today, we know GRBs come in two main varieties. Short bursts lasting less than 2 seconds are thought to be the result of two ultra-dense neutron stars merging in a cataclysmic collision, a violent dance that ends in the birth of a black hole. Long bursts, which can rage for minutes, are likely the final cries of massive stars collapsing in on themselves, their cores imploding into black holes while their outer layers are blasted outward at nearly the speed of light. But here's the kicker. Even though we've detected thousands of these bursts, pinpointing their exact origins remains a challenge. Some come from galaxies billions of light years away, their light traveling across the universe for eons before reaching us. And because they fade so quickly, scientists have only a narrow window to study them before they vanish forever. Yet every new detection brings us closer to unraveling their secrets and understanding how these fleeting explosions shape the cosmos in ways we're only beginning to grasp. If gamma-ray bursts are the universe's flashbulbs, hypernovas are the explosions behind them, supernovas cranked up to apocalyptic levels. These aren't just dying stars, they're stellar behemoths meeting their end in the most spectacular fashion imaginable. While a typical supernova marks the violent death of a star, a hypernova is that same cosmic detonation multiplied by 100, a supernova on steroids, packing enough raw energy to birth black holes and trigger gamma-ray bursts in one Earth-shattering finale. Take SN 1998 BW, one of the first hypernovas ever identified. When this colossal star in a distant galaxy met its end, it didn't just fade quietly. It erupted with such force that astronomers initially struggled to categorize it. The explosion released up to 100 times more energy than an ordinary supernova, hurling matter outward at nearly light speed while its core crumpled straight into a black hole. This wasn't just a star dying, it was a star self-destructing with enough fury to power entire galaxies momentarily. What makes hypernovas different from their less extreme cousins? It all comes down to the star's size and how it dies. Regular supernovas occur when mid-sized stars exhaust their fuel and collapse inward before rebounding in a brilliant explosion. But hypernovas come from stars so massive, think 30 times heavier than our Sun or more, that their collapse skips the rebound entirely. Instead, their cores implode directly into black holes, releasing insane amounts of energy in the process. The outer layers don't just explode outward, they're funneled into ultra-fast jets along the star's rotation axis, piercing through space like cosmic blowtorches. These jets are what scientists believe generate the accompanying gamma-ray bursts, making hypernovas the likely culprits behind those universe-spanning energy flashes. The aftermath is equally mind-blowing. While regular supernovas leave behind neutron stars or sprawling nebulas, hypernovas often leave nothing but a silent black hole and a legacy of scattered heavy elements forged in the explosion's unimaginable heat. Gold, platinum, uranium, the very materials that make up our planets and technology, were likely created in events like these, blasted across the cosmos by forces we're only beginning to measure. And here's the wild part, because hypernovas are so rare and short-lived, every new detection helps peel back another layer of their mysteries, revealing how the universe's most violent deaths also give birth to the building blocks of everything we know. Now imagine two city-sized stars, each so dense a teaspoon of their material would weigh 1 billion tons, locked in a death spiral. As they collide, they don't just explode, they detonate in a kilonova, a cosmic forge so intense it literally stitches together the heaviest elements in the universe. This isn't theoretical. In 2017, humanity witnessed this very event, GW 170817. The first time we've ever seen the aftermath of neutron stars merging in real time. The collision was so powerful it sent ripples through space-time itself, gravitational waves detected by observatories here on Earth. But the real magic happened in the aftermath. Forged in the unfathomable heat and pressure of that collision were vast clouds of gold, platinum, and uranium, enough to litter entire solar systems with precious metals. In fact, scientists estimate that a single kilonova can produce hundreds of Earth masses worth of gold alone. That means the ring on your finger, the circuitry in your phone, they likely owe their existence to a cataclysmic neutron star merger that occurred billions of years ago. What makes kilonovas so special isn't just their destructive power, but their creative force. Unlike supernovas, which scatter lighter elements like oxygen and carbon, kilonovas are the universe's primary factories for the heaviest elements. The collision's extreme conditions, trillions of degrees hot, with neutron-rich material flying at relativistic speeds, create the perfect environment for rapid neutron capture, or the R process. This is how atoms like gold and platinum are built, one neutron at a time, in a fraction of a second. The detection of GW 170817 was a watershed moment. Not only did it confirm kilonovas as the source of heavy elements, but it also marked the dawn of multi-messenger astronomy, where gravitational waves and light tell the same story. Telescopes around the world swiveled to catch the event's afterglow, revealing a vibrant, expanding cloud of radioactive debris glowing in ultraviolet, infrared, and X-rays. The data was so rich it solved decades-old mysteries like the origin of short gamma-ray bursts, which we now know are the jets unleashed during these mergers. Yet the most haunting realization, these events are vanishingly rare. Even in a galaxy as vast as the Milky Way, neutron star collisions might happen only once every 10,000 years. That makes every detection a precious glimpse into the universe's most extreme laboratories where gravity, nuclear physics, and quantum mechanics collide in a spectacle that quite literally builds the world around us. Hidden at the heart of some of the universe's most luminous objects are cosmic powerhouses capable of launching jets so energetic they defy physics as we know them. Quasars, the brilliant cores of distant galaxies, are more than just dazzling beacons. They're the engines behind relativistic jets, narrow streams of superheated plasma racing outward at nearly the speed of light, stretching thousands upon thousands of light years into the void. These aren't just celestial fireworks, they're nature's own particle accelerators, operating on scales that make even the most advanced human-built machines seem microscopic. The secret behind these jets lies in the monstrous supermassive black holes lurking at the centers of quasars. As matter spirals toward the black hole's event horizon, it doesn't just vanish quietly. Instead, it forms a swirling, superheated disk of gas and dust glowing with the intensity of trillions of suns. But some of that material doesn't fall in. It gets funneled outward along the black hole's poles, accelerated by unimaginable magnetic fields to velocities approaching light speed. The result, twin beams of energized particles shooting into space like cosmic blowtorches, visible across billions of light years. These jets do more than just dazzle, they sculpt the universe around them. When a quasar's jet plows through surrounding gas and dust, it can trigger or halt star formation in its host galaxy, effectively dictating whether new suns are born or snuffed out. Some jets are so powerful they punch through entire galaxy clusters, carving out vast bubbles in intergalactic space. And because quasars are so luminous, their jets serve as cosmic lighthouses, allowing astronomers to study the earliest epochs of the universe. The light we see from some quasars embarked on its journey when the cosmos was less than a tenth of its current age, offering a window into a time when galaxies were still in their infancy. Detecting these jets isn't easy, but modern technology has given us unprecedented glimpses. Radio telescopes capture the high-energy particles as they twist in magnetic fields, while X-ray observatories reveal the shockwaves where jets collide with interstellar gas. And sometimes, when a jet happens to point directly at Earth, we witness a phenomenon called a blazar, an outburst so intense it temporarily outshines every other source in its galaxy. Yet for all we've learned, mysteries remain. How exactly do black holes channel so much energy into these focused beams? Why do some quasars produce jets while others don't? Each discovery peels back another layer, revealing how these titanic structures not only illuminate the cosmos but also shape its very evolution. If neutron stars are the universe's heavyweights, magnetars are their volatile cousins, cosmic powerhouses with a temper. These aren't just dense remnants of dead stars, they're celestial monsters wielding magnetic fields so strong they could strip the information off a credit card from halfway across the galaxy. We're talking about forces a quadrillion times more powerful than Earth's magnetic field, so intense they warp the very fabric of space around them. But what happens when a magnetar snaps? The result is a starquake, a seismic event on the surface of the star so violent it unleashes a flare of energy capable of frying satellites and scrambling Earth's ionosphere, even from 50,000 light-years away. The most dramatic example, December 27, 2004. A blast of gamma rays and X-rays from the magnetar SGR 1800-620 struck Earth with the force of a solar flare, despite originating far outside our galaxy. For a fraction of a second, it outshone the full moon, bathing our planet in radiation detectable by satellites meant to monitor nuclear explosions. The true source of these eruptions lies in the magnetar's crust. Imagine the surface of a neutron star, a crystalline shell under unimaginable strain, locked in place by a magnetic field strong enough to distort atoms. When that crust cracks under pressure, it releases pent-up energy like a cosmic rubber band snapping, vibrating the star like a bell and triggering a superflare. These quakes don't just release light, they unleash tsunamis of charged particles rippling through space, disrupting radio communications and even causing auroras on worlds light years away. What makes magnetars even stranger is their unpredictability. Unlike pulsars, which tick with the precision of atomic clocks, magnetars erupt without warning. Some flare multiple times in a decade, others remain silent for centuries, and when they do awaken, their outbursts can last from milliseconds to minutes, enough time to rewire the magnetic environment of an entire star system. Yet these violent events aren't just destructive. They are also cosmic laboratories. By studying magnetar flares, scientists probe the limits of physics, testing how matter behaves under conditions impossible to replicate on Earth. Every eruption peels back another layer of mystery, revealing how the universe's most extreme magnets shape the cosmos in ways we're only beginning to understand. Black holes don't always swallow stars whole. Sometimes they tear them apart in a slow, spectacular fashion. Known as tidal disruption events, these cosmic shredding sessions occur when a star drifts too close to a supermassive black hole's gravitational grip. The star doesn't stand a chance. The side nearest the black hole feels a far stronger pull than the opposite side, stretching the star like taffy until it snaps apart in a process called spaghettification. But destruction isn't the end, it's the beginning of a brilliant light show. As the star's debris spirals inward, it heats up to millions of degrees, unleashing a flare so bright it can outshine the star's entire host galaxy for months. Take Assassin 15LH, the most luminous tidal disruption event ever recorded. When this star met its doom in a distant galaxy, the explosion was so intense astronomers initially mistook it for an impossibly powerful supernova. At its peak, it blazed with the brightness of 570 billion suns, 20 times more luminous than the entire Milky Way. But the real shock came when researchers realized the black hole responsible shouldn't have been capable of such an extreme outburst based on its size. Conventional models suggested the flare should have been weaker, leaving scientists scrambling for explanations. Some theorized the black hole was spinning at near light speed, amplifying the energy output. Others proposed the presence of a hidden jet or an intermediate mass black hole defying expectations. What makes tidal disruption events so fascinating isn't just their violence, it's what they reveal. The flares act like cosmic X-rays, illuminating the otherwise invisible black holes at the centers of galaxies. By studying the light emitted during these events, astronomers can measure the black hole's mass, spin, and even the composition of the devoured star. And because the flares fade slowly, they offer a rare extended window to observe these elusive predators in action, yet mysteries linger. Why do some TDs produce powerful X-rays while others glow predominantly in ultraviolet? Could magnetic fields or debris collisions explain the variations? Each new discovery adds another piece to the puzzle, proving that even in death, stars have much to teach us about the darkest corners of the universe. Some stars don't just die, they erase themselves from existence in explosions so violent they leave no trace behind. Enter pair instability supernovas, the universe's ultimate vanishing act. These aren't ordinary stellar deaths. They're thermonuclear detonations so thorough they vaporize every last atom of the star, leaving behind no black hole, no neutron star, just empty space where a giant once burned. This bizarre fate awaits only the most massive stars imaginable, celestial titans weighing at least 150 times our sun's mass. Their demise begins deep in the core, where temperatures soar so high that gamma-ray photons, normally just carriers of energy, transform into something else entirely. When the heat crosses a critical threshold around 1 billion degrees, These photons spontaneously convert into electron-positron pairs, matter and antimatter, springing into existence from pure energy. This sudden particle creation robs the core of its outward pressure, like pulling the supports from beneath a collapsing building. What happens next is catastrophic. With radiation pressure gone, gravity takes over in an instant. The star's core implodes violently, but instead of bouncing back as in a normal supernova, the collapse triggers runaway fusion. Oxygen and silicon ignite in rapid succession, releasing so much energy that the entire star blows apart like a cosmic grenade. No fragment survives. Every ounce of stellar material gets vaporized in the inferno, scattering heavy elements across space in an explosion visible across the universe. These events are vanishingly rare today, but they may have been the fireworks that lit up the early cosmos. In the universe's first few 100 million years, when massive stars formed more readily, pair instability supernovas could have been relatively common. Their absence today tells a story. The modern universe simply doesn't make stars big enough to meet this fate anymore. Yet when they did occur, their impact was profound. The iron, oxygen, and other elements they spewed forth became the raw materials for future stars, planets, and ultimately, life itself. The ghostly nature of these explosions makes them incredibly hard to study. Without a compact remnant like a neutron star to mark the spot, astronomers rely on telltale signs in the light curve, the specific way these supernovas brighten and fade. One promising candidate, SN 2007bi, matched key predictions: its light profile, its lack of lingering X-ray sources, and the staggering amount of nickel-56 it produced, a radioactive isotope that acts as a cosmic stopwatch for the explosion's physics. Perhaps the most mind-bending implication: if stars get too massive, above maybe 260 solar masses, gravity overwhelms even this explosive finale. In those cases, the entire star collapses directly into a black hole without a supernova at all. It simply winks out. This delicate balance between total annihilation and silent collapse makes pair instability supernovas one of the universe's most elusive and fascinating phenomena. A brief, brilliant flash marking not just a star's death, but its complete and utter erasure from the cosmic record. At the heart of almost every large galaxy lurks a sleeping giant, a supermassive black hole with the power to transform its entire home into the brightest object in the universe. When these monsters wake up, they don't just snack on passing stars, they devour gas, dust, and entire solar systems, unleashing so much energy they can outshine 1 trillion suns. These are active galactic nuclei, or AN, the universe's ultimate power stations, and their brilliance isn't just spectacle, it's a cosmic engine reshaping galaxies. Not all AGN are created equal. Take Seyfert galaxies, for instance. These relatively quiet neighbors host black holes that feed steadily, their swirling accretion disks glowing with soft X-rays and ultraviolet light. They're like campfires compared to the infernos of quasars. AGN so luminous they drown out every star in their host galaxies. But the real showstoppers are blazars, AGN with jets pointed straight at Earth, their particle beams accelerated to near light speed by magnetic fields twisted tighter than a tornado. When these jets flare, they can flicker in brightness over mere hours, proving the energy originates from regions no larger than our solar system. What powers these cosmic lighthouses? It all comes down to gravity's most extreme chemistry set. As matter spirals toward the black hole, friction heats it to millions of degrees, transforming it into a glowing plasma. But here's the twist: not all that material gets swallowed. Magnetic fields whip some of it into jets that shoot outward, carrying energy equivalent to thousands of exploding stars every second. The efficiency is staggering. Up to 40% of the infalling mass gets converted directly into energy, dwarfing the puny 0.7% yield of nuclear fusion that powers stars. The impact of AGN extends far beyond their dazzling light shows. Their jets can carve cavities in intergalactic gas, halting star formation across entire galaxy clusters. Some theorists even argue that without AGN regulating growth, galaxies would grow too fat, too fast, collapsing under their own weight. Yet for all their violence, AGN also serve as cosmic measuring sticks. Because they're visible across billions of light years, their light carries fingerprints of the early universe, revealing how black holes and galaxies grew together in the cosmic dawn. But mysteries remain. Why do some black holes feast while others starve? What triggers their explosive awakenings? Every new observation peels back another layer, proving these galactic powerhouses aren't just destructive, they're the architects of the universe's grandest structures. While the universe's grandest explosions play out across cosmic distances, our very own sun reminds us that stellar violence isn't limited to distant galaxies. Solar flares' sudden, localized eruptions of electromagnetic radiation may pale in comparison to hypernovas or quasars, but their proximity makes them a force to reckon with. At their most extreme, these outbursts unleash energy equivalent to billions of hydrogen bombs in mere minutes, categorizing them as X-class flares, the solar system's most explosive weather events. The mechanics behind these eruptions are as fascinating as they are terrifying. Twisted magnetic fields near sunspots snap like overstretched rubber bands, accelerating charged particles to near light speed and heating the sun's corona to tens of millions of degrees. The flash of X-rays and ultraviolet radiation reaches Earth in just 8 minutes, ionizing our upper atmosphere and disrupting radio signals. But the real danger often follows hours or days later. Coronal mass ejections, or CME, billion-ton clouds of magnetized plasma hurled into space at speeds topping several million miles per hour. When these storms collide with Earth's magnetic field, the results can be anything from dazzling auroras to global technological chaos. History offers a chilling case study, the Carrington event of 1859. Named after astronomer Richard Carrington, who witnessed the accompanying solar flare through his telescope, this geomagnetic storm supercharged telegraph systems worldwide. Operators reported sparks leaping from their equipment, some even sending messages with batteries disconnected, powered solely by atmospheric currents induced by the storm. Northern lights blazed as far south as Cuba, turning night skies blood red. Today, a similar event would wreak far greater havoc. Modern power grids, satellites, and undersea cables, all vulnerable to induced currents, could face cascading failures, potentially knocking out GPS, communications, and electricity for weeks or months. The stakes became starkly clear in July 2012 when a Carrington-level CME narrowly missed Earth. Satellites recorded an eruption packing enough punch to cripple global infrastructure, but its trajectory spared us. NASA estimates the economic impact of a direct hit could exceed $2 trillion in the first year alone. Unlike distant cosmic explosions, solar storms offer no spectacle, just silent, invisible forces bending technology to their will. Yet for all their destructive potential, they also serve as humbling reminders. Even our local star, a middling dwarf by cosmic standards, holds enough power to reshape civilization in a single, fiery breath. Among the cosmos' strangest signals are fast radio bursts, fleeting blips of radio waves so powerful they outshine entire galaxies in milliseconds, then vanish without a trace. These FRBs, as astronomers call them, last barely longer than the blink of an eye, but pack as much energy as 500 million suns. Their discovery in 2007 sent shockwaves through the scientific community, not just for their intensity but for their mystery. Where do they come from? What could possibly produce such a brief, dazzling flash across the universe? One of the biggest breakthroughs came with FRB 121102, the first repeating fast radio burst ever detected. Unlike most FRBs that fire once and go silent, this one near a dwarf galaxy 3 billion light-years away flickers like a cosmic strobe light, erupting unpredictably every few months. Its repeating pattern ruled out cataclysmic explanations like colliding neutron stars events that can't happen twice from the same spot. Instead, the culprit might be a highly magnetized neutron star or even a young magnetar throwing violent tantrums as it spins. Some bursts from 12-1102 show bizarre, twisted radio waves evidence they've passed through an incredibly strong magnetic field, like one surrounding a black hole or a nebula of superheated plasma. Yet not all FRBs are so easily explained. Some appear completely isolated with no visible host galaxy or lingering afterglow. Others arrive with a lower frequency chirp, suggesting they've traveled through vast cosmic distances, their signals stretched by the expanding universe. And then there's FRB 2024, a burst from our own galactic backyard, originating within the Milky Way and linked definitively to a known magnetar. This discovery proved at least some FRBs stem from these ultramagnetic stars, but the sheer variety of bursts leaves room for wilder possibilities. Could some be produced by cosmic strings, hypothetical defects in spacetime itself? Or, as a handful of scientists have speculated, might advanced civilizations be harnessing black holes to power interstellar beacons? Whatever their source, FRBs are more than just cosmic oddities. Their fleeting signals act like interstellar probes, carrying encoded details about the material they've traversed. By analyzing how these waves disperse, scientists can map the universe's hidden matter, the diffuse gas between galaxies that's nearly impossible to detect otherwise. Each new burst adds another piece to the puzzle, revealing how the universe's most enigmatic whispers might hold the key to understanding its darkest corners. 30 years ago, a star died right in our cosmic backyard, and humanity got front-row seats to the most studied supernova in history. Supernova 1987 wasn't just another explosion. It was a gift from the universe, unfolding a mere 168,000 light-years away in the Large Magellanic Cloud. For the first time, modern telescopes and detectors could scrutinize a stellar demise up close, transforming theoretical models into vivid reality. The detonation began with a silent whisper, 11 neutrinos detected underground in Japan and the United States, ghostly particles fleeing the collapsing core hours before visible light erupted. This was the smoking gun, proof that supernovas really do blast neutrinos outward as their cores implode, just as physicists had predicted. Those 23 neutrinos, a handful of signals lasting seconds, carried more information about stellar death than decades of speculation. They revealed the birth of a neutron star, its formation hidden behind the expanding debris of the shattered star. Then came the light show. Over months, SN 1987 brightened until it outshone every other star in its galaxy, visible to the naked eye from Earth. But the real marvel was what followed, not a fading spark, but an evolving laboratory. As the explosion's shockwave slammed into pre-existing rings of gas, likely ejected by the star in its final millennia, it lit them up like a cosmic bullseye. Hubble's razor-sharp images captured this glowing trio of rings in unprecedented detail, their structure defying expectations. No one had predicted a dying star would sculpt such intricate farewell artwork. Decades later, those rings keep teaching us. The shockwave's collision with the inner ring, first spotted in the 1990s, created a fireworks display of hotspots. Knots of gas heated to millions of degrees, sparkling like diamonds strung along a celestial bracelet. X-ray observatories saw the aftermath. Heavy elements forged in the explosion, including titanium-44, a radioactive tracer of the supernova's nuclear recipes. And somewhere in the wreckage, the neutron star that theory insists must exist still eludes detection, possibly shrouded by dust or collapsed further into a black hole. What makes SN 1987 so special isn't just its proximity, it's the way it keeps giving. Every new telescope, from Chandra to JWST, peers at its remnants and finds fresh puzzles. The latest infrared images reveal crescents of warm dust where models predicted none, hinting at asymmetries in the blast. Meanwhile, the shockwave continues its slow march outward, plowing through interstellar space like a cosmic tide, showing us how supernova remnants seed galaxies with the stuff of planets and life. This one explosion rewrote textbooks, proving that sometimes the universe hands us a masterpiece wrapped in fire and mystery. Every second, invisible bullets tear through space at nearly the speed of light cosmic rays, atomic fragments hurled across the universe with energies that make particle accelerators look like toys. Some pack the punch of a fastball pitch, all condensed into a single proton smaller than an atom. Imagine that, a subatomic speck carrying enough kinetic energy to power a light bulb for seconds, a concentration of power so extreme it defies common sense. Where do these atomic cannonballs come from? For decades, that question baffled scientists. Some cosmic rays are clearly born from our own sun, but the real enigmas are the ultra-high-energy ones, particles screaming through space with energies exceeding 100 exaelectron volts. That's millions of times more powerful than anything produced in the Large Hadron Collider. The leading suspects include supermassive black holes revving up particles in their jets, or perhaps hypernovas, those stellar explosions we explored earlier, acting as natural particle accelerators. Yet when researchers trace their paths backward, many seem to come from nowhere, literally. Some arrive from voids between galaxies, regions so empty they shouldn't host anything capable of such violence. Enter the Pierre Auger Observatory, a cosmic ray detective agency sprawled across 3,000 square kilometers of Argentine grassland. Instead of telescopes, it uses 1,600 water tanks spaced like a giant grid, waiting for the telltale blue flashes produced when a cosmic ray smashes into Earth's atmosphere. These collisions create particle showers, avalanches of secondary particles that rain down over miles, revealing the original ray's energy and direction. The observatory's findings have been groundbreaking. By mapping thousands of high-energy events, it confirmed something startling. The most energetic cosmic rays don't come evenly from all directions. Instead, they cluster around active galaxies, those with supermassive black holes devouring matter and spewing jets. But here's the twist: even as the Auger data points to black holes as prime suspects, the numbers don't quite add up. The particles' energies are too high, their acceleration seemingly breaking known physics. Some theorists speculate they're boosted by shockwaves in intergalactic plasma, while others propose exotic origins, cosmic strings, decaying dark matter, or even defects in space-time itself. And there's another puzzle. The universe should have put a speed limit on these particles. At extreme energies, protons should lose steam by colliding with the faint glow of cosmic microwave background radiation, a phenomenon called the Greisen-Zatsepin-Kuzmin-Gzk cutoff. Yet a handful defy this limit, arriving with energies that should be impossible over long distances. What does it all mean? For starters, cosmic rays are more than just space oddities, they're messengers. By studying them, we probe environments too hostile to observe directly, from the hearts of quasar jets to the voids between superclusters. They might even hold clues about the universe's most elusive substance, dark matter. Some models suggest certain cosmic rays could be debris from WIMP, weakly interacting massive particles annihilating in distant space. Every detection is a piece of the puzzle, helping us decode how the universe's most violent engines shape the fabric of reality itself. Imagine a star so wild it sheds entire suns' worth of mass, not in explosions, but in relentless supersonic winds. Wolf-Rayet stars are cosmic gales incarnate, stellar behemoths in their final death throes, blasting their own atmospheres into space at speeds topping 9 million miles per hour. These aren't gentle breezes, they're plasma hurricanes violent enough to strip planets to their cores, fueled by nuclear furnaces running on borrowed time. What makes these stars so extreme? Born weighing 40 times more than our Sun, Wolf-Rayet stars burn through their fuel at a breakneck pace, living fast and dying young. After exhausting hydrogen in their cores, they begin fusing heavier elements: helium, carbon, oxygen. in layered shells like a cosmic onion burning from the inside out. But the real drama unfolds on their surfaces. Radiation pressure from these intense fusion reactions blows their outer layers into space, exposing searing hot cores hotter than 200,000 degrees. The result, a star shrouded in its own disintegrating atmosphere, ejecting a solar mass every 100,000 years, equivalent to losing an Earth's worth of material every few days. The chemical fingerprints of these winds are unmistakable. Rich in helium, nitrogen, and carbon but devoid of hydrogen, they paint interstellar space with the ashes of nuclear fusion. The Carina Nebula offers a stunning example. WR25, one of the most massive stars known, churns its surroundings into glowing tendrils of ejected material. These nebulous wreaths aren't just beautiful, they're stellar gravestones, marking where a giant is shedding its skin before the final cataclysm. But Wolf-Rayet stars don't just fade quietly. Many are prime suspects for gamma-ray burst progenitors, especially those stripped to their bare metal cores. When these stars finally collapse, their lack of hydrogen envelopes allows relativistic jets to punch straight through, potentially triggering long GRBs. The link was cemented in 2006 when GRB 060614 erupted. Its afterglow spectra revealed a wolf ray, its distinct chemistry, the smoking gun connecting these stars to one of the universe's most violent phenomena. Their legacy extends beyond destruction. By spewing heavy elements forged in their cores, Wolf-Rayet stars act as galactic alchemists. The carbon in your DNA, the oxygen you breathe, much of it likely passed through the winds of these dying giants before being incorporated into new generations of stars and planets. Even in death, they shape the cosmic ecosystem, proving that sometimes the universe's most violent winds sow the seeds for everything that follows. The jets erupting from supermassive black holes aren't just streams of hot gas, they're nature's ultimate particle accelerators, funneling matter outward with such violence that they stretch nearly the length of entire galaxies. Take M87 star, the first black hole ever imaged by the Event Horizon Telescope. While its now famous silhouette showed the shadow of its event horizon, the real spectacle lies in the relativistic jet shooting from its poles, a column of plasma stretching 5,000 light-years into space, visible even from 55 million light-years away. How does a black hole, infamous for sucking everything in, become the universe's most powerful slingshot? The secret lies in the chaotic whirlpool of its accretion disk. As matter spirals toward the event horizon, friction heats it to billions of degrees, creating a magnetized soup of charged particles. But not all this material crosses the point of no return. Some gets caught in the black hole's swirling magnetic fields, which act like cosmic rails, channeling particles outward along the rotation axis at velocities exceeding 99% light speed. The process resembles water spiraling down a drain, only to get squeezed out through two fire hoses at the top and bottom. The acceleration mechanism called the Blandford-Zenagic process taps into the black hole's spin itself, converting rotational energy directly into particle motion. It's staggeringly efficient. For context, nuclear fusion in stars converts less than 1% of mass into energy, while these jets can achieve efficiencies over 40%. The result, beams so energetic they punch through intergalactic space for millions of years, glowing in radio waves as their electrons spiral around magnetic field lines. But M87 star's jet has another bizarre feature. It's not perfectly straight. High-resolution images reveal a corkscrew twist, evidence of precession, a wobble in the black hole's spin axis that might be caused by a second, smaller black hole orbiting nearby. This dance warps space-time itself, bending the jet into a helical shape like water from a spinning lawn sprinkler. These jets aren't just spectacular, they're galactic architects. When they plow into surrounding gas clouds, they can trigger or suppress star formation, effectively governing cosmic evolution. And for astronomers, they serve as laboratories for testing general relativity under conditions impossible to recreate on Earth. Every kink, every shockwave in these relativistic death rays tells a story of hidden physics, violent origins, and the unseen forces shaping our universe. Rising like ghostly titans from the heart of our galaxy, two colossal orbs of gamma radiation tower above and below the Milky Way's disk, each stretching 25,000 light-years into the void. These are the Fermi bubbles, named after the telescope that discovered them in 2010, and they're anything but subtle. Imagine a structure so vast it could swallow our entire solar system 1,000 times over, glowing with the aftermath of violence so extreme it still lingers after millions of years. What could have sculpted these cosmic megastructures? The leading theory points to our galaxy's silent predator, the supermassive black hole Sagittarius, a star. While today it's a sluggish giant barely sipping on wisps of gas, evidence suggests it wasn't always so quiet. Roughly 2 million years ago, it may have awakened in a feeding frenzy, devouring stars or gas clouds with such ferocity that it launched jets of plasma straight through the galactic poles. Like a blowtorch-piercing smoke, these jets would have punched through the Milky Way's halo, leaving behind bubbles of superheated gas that now emit gamma rays as trapped particles collide. But there's a twist. The bubbles aren't just relics, they're still crackling with energy. Observations reveal their edges are razor-sharp, as if the structure's being actively maintained against the pressure of intergalactic space. Some researchers argue this points to intermittent black hole activity, like a dormant volcano occasionally belching smoke, while others propose an even wilder origin, a swarm of dark matter annihilations near the galactic center, releasing energy in sporadic bursts. The clues don't stop there. In 2020, astronomers spotted a matching pair of X-ray bubbles using the E-Rosetta telescope, perfectly aligned with the Fermi structures but slightly larger. This double-layered phenomenon suggests the outburst wasn't a one-time event, but a stuttering series of eruptions over millennia. Imagine a black hole clearing its throat multiple times, each cough adding another shell to the expanding aftermath. What makes these bubbles truly extraordinary is their intimacy. Unlike distant quasars or hypernovas, they're part of our cosmic neighborhood, a fossilized record of the Milky Way's violent adolescence. Their very presence hints that even seemingly quiet galaxies like ours have explosive pasts, and that the next outburst might not be as ancient as we think. After all, 2 million years is a blink in cosmic time. If Sagittarius, a star, erupted once, what's stopping it from waking up again? For now, the bubbles loom silently, a reminder that our galaxy's heart still holds secrets written in gamma-ray light. Most stars brighten when they explode, but our Coronae Borealis stars do the exact opposite. These cosmic oddballs lurk quietly in the night sky before suddenly, without warning, plunging into darkness as if someone flipped a switch. Their dimming isn't caused by some external force eclipsing them. No, these stars literally shroud themselves in thick clouds of carbon dust, self-sabotage on a stellar scale. Discovered back in 1795, the prototype star, our Coronae Borealis, gave astronomers their first taste of this bizarre phenomenon. Unlike supernovas that announce their destruction with brilliant flares, these stars perform a vanishing act, fading by factors of hundreds or even thousands over weeks or months before gradually recovering. The culprit, their own atmospheres turning against them. Our Coronae Borealis stars are carbon factories, packing helium-burning cores surrounded by layers rich in carbon and little hydrogen. Occasionally, this carbon condenses into soot-like particles right in the star's upper layers. When enough accumulates, it forms an opaque curtain that blocks the star's light entirely, a cosmic magic trick where the performer disappears in a cloud of their own making. What makes these stars truly fascinating is their unpredictability. Some might go years between dimming episodes, while others fade multiple times in quick succession. Take RY Sagittarii, one of the brightest examples. In 2005, it plunged from naked eye visibility to telescopic obscurity in just 40 days. its carbon dust cloud so dense it absorbed nearly all the star's light. Yet months later, as the dust dispersed under the star's radiation pressure, it brightened again only to repeat the cycle unpredictably. The aftermath of these anti-novas is just as strange. Unlike supernova remnants that glow for millennia, the carbon dust from our Coronae Borealis stars doesn't linger. Instead, it's blown away by stellar winds, spreading carbon atoms through space, the same carbon that might eventually form diamonds on distant planets or become part of organic molecules. In a way, these stars are cosmic recyclers, manufacturing and scattering life's essential elements not with a bang, but with a self-inflicted shadow. Yet mysteries remain. Why do some carbon-rich stars behave this way while others don't? Could magnetic fields or hidden companions trigger the dust formation? Each dimming event offers fresh clues, proving that sometimes the universe's most explosive secrets come wrapped in darkness rather than light. Some stellar explosions don't come from stars dying. They come from stars colliding in violent embraces that rewrite their destinies. Luminous red novas are cosmic fireworks born from mergers, when two stars spiral too close and ignite in a fiery dance that outshines entire solar systems. These aren't the universe's most energetic blasts, but they're among its most visually stunning, painting interstellar space with glowing shrouds of expelled material. Take V838 Monocerotes, the poster child for these mid-energy explosions. In early 2002, this unremarkable star in the constellation Monoceros abruptly brightened by a factor of 1 million, becoming one of the Milky Way's most luminous objects virtually overnight. At first, astronomers assumed it was a typical nova, a white dwarf erupting from accreted material, but the truth was far more dramatic. Instead of fading quickly, V838 Mon's light lingered, then transformed. Over months, it developed a spectacular light echo as its illumination bounced off surrounding dust shells, revealing structures ejected during earlier phases of the star's life. Hubble's images of this phenomenon look like a cosmic inkblot test, with ripples of light expanding outward like shockwaves frozen in time. What causes these eruptions? Unlike supernovas born from collapsing cores, luminous red novas stem from stellar mergers, usually a binary pair where one star engulfs its companion. As the smaller star spirals inward, friction heats both bodies to extreme temperatures, triggering runaway nuclear reactions in their shared outer layers. The resulting explosion isn't powerful enough to obliterate the stars completely, but it's sufficient to blast their merged atmospheres into space, creating the signature red glow of cooling hydrogen and ionized metals. The aftermath often defies expectations. In V838 Mon's case, the merged object didn't form a neutron star or black hole. Instead, it settled into a bizarre supergiant state, its surface temperature yo-yoing unpredictably. Other mergers, like the 2015 event in the Andromeda Galaxy catalogued as M31LRN, left behind a single bloated star surrounded by a nebula of ejected material rich in lithium, an element rarely seen in such quantities. This hints that stellar smash-ups might be key suppliers of lithium in the universe, the same element powering your smartphone batteries. But perhaps the most tantalizing aspect of these explosions is their role as cosmic Rosetta Stones. By studying light echoes, the delayed reflections of the initial flash, astronomers can reconstruct 3D maps of the dust clouds surrounding merged stars. It's like cosmic sonar, using light instead of sound to probe structures otherwise invisible. Each new luminous red nova peels back another layer of mystery, revealing how even the universe's quieter explosions can rewrite the rules of stellar evolution. Deep in the heart of our galaxy, an unexplained glow of gamma rays pulses with a rhythm that defies conventional astronomy. Known as the galactic center excess, this mysterious emission has scientists probing one of the most tantalizing possibilities in modern physics. Could we be witnessing dark matter annihilating itself? Unlike the spectacular explosions of hypernovas or quasars, this signal is subtle, a whisper of high-energy light concentrated around Sagittarius A. Yet if confirmed, it might reveal the invisible scaffolding of the cosmos. The theory hinges on dark matter's hypothetical nature. While we've mapped its gravitational influence for decades, binding galaxies together, sculpting the cosmic web, its particles have never been directly observed. Some models suggest certain dark matter particles could be their own antimatter counterparts. If true, when two such particles collide, they'd annihilate in a burst of energy, producing gamma rays as byproducts. The galactic center, dense with dark matter, would be the perfect arena for these invisible fireworks. Intriguingly, the excess's energy signature matches predictions for WIMP, weakly interacting massive particles, a leading dark matter candidate. Simulations show WIMP with masses around 31 to 40 gigaelectronvolts could produce gamma rays at the exact energies observed. But the plot thickens. The signal's spatial distribution doesn't align neatly with known astrophysical sources like pulsars. Instead, it spreads smoothly across the galactic core, just as dark matter halos should. Skeptics counter with alternative explanations. Millisecond pulsars, too faint to detect individually, might collectively mimic the signal. Or perhaps Sagittarius A's past activity left behind a fog of high-energy particles. Yet neither fully accounts for the data's peculiarities. The debate underscores a deeper truth. The galactic center excess is either a Rosetta Stone for dark matter or a cosmic Rorschach test, revealing how eagerly we project hopes onto ambiguous data. Future observatories like the Cherenkov telescope array aim to resolve the mystery by pinpointing the gamma ray's origins with unprecedented precision. A definitive link to dark matter would revolutionize physics, proving that the universe's hidden bulk isn't just passive scaffolding, but an active participant in the high-energy cosmos. Until then, the excess remains a ghostly clue, reminding us that the universe's most explosive secrets might be written in particles we've yet to see. Every explosion we've explored pales in comparison to the one that started it all. The Big Bang, the ultimate cosmic detonation. This wasn't just an eruption of matter and energy, it was the birth of space and time itself, a singularity of infinite density suddenly expanding into the universe we know today. Unlike supernovas or gamma-ray bursts which fade within moments or millennia, the afterglow of the Big Bang still lingers, faint but detectable, in every direction we look. That afterglow is the cosmic microwave background radiation, a whisper of heat left over from the universe's fiery infancy. Picture this: 380,000 years after the Big Bang, the cosmos had cooled enough for protons and electrons to combine into hydrogen atoms, releasing a flash of light. That light, once blazing at thousands of degrees, has stretched with the expanding universe into microwave wavelengths, now just a few degrees above absolute zero. Satellites like Planck and Cobe have mapped this radiation with stunning precision, revealing tiny temperature fluctuations, cosmic fingerprints of density variations that would later seed galaxies, stars, and everything we see around us. But the real mind-bending aspect isn't just the afterglow, it's the energy scales involved. In the first fractions of a second, temperatures soared past 100 trillion degrees, hot enough to melt protons and neutrons into a seething quark-gluon plasma. Forces we now consider separate electromagnetism, the strong and weak nuclear forces, were unified into a single, incomprehensible superforce. Even time behaved differently. The universe expanded faster than light itself during a period called inflation, doubling in size at least 90 times in less than a trillionth of a second. Yet for all its violence, the Big Bang wasn't chaotic in the way we think of explosions. Its expansion was eerily precise, fine-tuned to a degree that still baffles physicists. The density of matter in those early moments had to be balanced to 1 part in 100,000 billion. Any more, and the universe would have collapsed back into a black hole, any less, and matter would have scattered too thinly for galaxies to form. This delicate equilibrium hints at something deeper. The Big Bang wasn't just a random event. It was the universe's first and most carefully orchestrated explosion, setting the stage for everything that followed, including us. And here's the kicker, we're still inside that explosion. The universe keeps expanding, stretching the fabric of space itself, carrying galaxies away from each other like embers drifting apart in the aftermath of a blast. The Big Bang isn't just history, it's the ongoing story of the cosmos, written in the language of light, matter, and the echoes of an unfathomable beginning. For centuries, astronomers pictured supernovas as perfect spheres, symmetrical explosions where a dying star blasted its material outward in all directions with mathematical precision. But modern telescopes have shattered that illusion, revealing a far messier reality. Many of these cosmic detonations are lopsided, chaotic events, spraying debris in uneven jets and leaving behind mangled remnants that careen through space like celestial shrapnel. The first clues came from studying the aftermath. When researchers examined supernova remnants like Cassiopeia A, they found twisted knots of gas and metals flung outward at different speeds, forming jagged structures instead of smooth shells. Then came the pulsars, ultra-dense neutron stars born from supernova collapses racing across the galaxy at hundreds of miles per second, their paths defying simple explanations. These kicked pulsars shouldn't exist if their parent explosions were symmetrical. Their blistering speeds hinted at some monstrous imbalance during their violent births. The smoking gun arrived with stripped envelope supernovas, stars that had shed their outer hydrogen layers before exploding. Observations showed their light curves rising and fading unevenly, as if viewed from different angles. Spectra revealed material ejected faster in one direction than another, clear evidence of jets punching through the star's carcass. Some explosions, like SN 2018 JV, even displayed polarized light, its waves aligned in a way that screamed asymmetry, like a flashlight beam shining straight at Earth rather than an even glow. What causes this cosmic imbalance? The answer lies in the chaos of collapse. As a massive star's core implodes, it doesn't crumple evenly. Convection currents, magnetic fields, and violent neutrino outbursts create turbulent conditions where matter and energy funnel outward along preferred paths, like water spiraling down a drain. In extreme cases, this lopsided force might accelerate the newborn neutron star to runaway speeds, explaining those high-velocity pulsars. For black holes, asymmetry could determine their spin, a wobbly collapse imprinting a chaotic rotation that shapes how they devour matter later. The implications stretch beyond stellar death. Asymmetric supernovas scatter heavy elements unevenly, seeding some regions of space with more planet-building material than others. Their jets might even trigger star formation in nearby gas clouds, proving that even in their final moments, stars don't just explode, they sculpt the universe with their dying breaths. And every twisted remnant we find, it's a testament to the beautiful, messy truth. Symmetry might be pleasing to the eye, but the cosmos thrives on chaos. Pulsars are often called the universe's most precise clocks, spinning with such metronomic regularity that their radio pulses can time Earth's rotation better than atomic clocks. But every now and then, these cosmic timekeepers do something bizarre. They suddenly speed up. These events, known as pulsar glitches, send shockwaves through astrophysics literally. Imagine a skater pulling their arms in mid-spin and accelerating impossibly fast, except here, the skater is a city-sized neutron star weighing more than our sun, and the arms are its own fracturing crust. The most famous example, the Vela pulsar, a stellar corpse spinning 11 times per second in our galactic backyard. In 1969, astronomers watched in disbelief as Vela's rotation rate abruptly jumped by 1 part in a million, a tiny but monumental shift for an object normally stable to 15 decimal places. Since then, nearly 300 glitches have been catalogued across dozens of pulsars, each offering clues to the extreme physics inside these dense remnants. The leading explanation, starquakes, deep beneath a pulsar's iron-rich crust, its superfluid core, a bizarre quantum liquid with zero viscosity, rotates slightly faster than the crust above. Normally, magnetic fields keep the two locked in sync, but as the star gradually slows over millennia, losing energy to radiation and particle winds, strain builds until crack. The crust fractures like a tectonic plate, suddenly shrinking the star's diameter by micrometers. This tiny contraction causes the pulsar to spin faster, just as a figure skater accelerates when pulling their arms in. The released energy can be staggering, equivalent to a magnitude 23 earthquake if it happened on Earth. But glitches aren't just about crust snapping. Some pulsars, like the crab in Taurus, exhibit slow glitches where the speed-up occurs gradually over weeks, hinting at a different mechanism, possibly vortices in the superfluid core unpinning from the crust's interior. Others, like J0537-6910 in the Large Magellanic Cloud, have shown anti-glitches where they inexplicably slow down. These outliers suggest pulsar interiors are far more dynamic than we thought, with competing processes, superfluid turbulence, magnetic reconnection, even quantum vortex tangles vying for control. The connection to magnetars adds another layer of intrigue. These ultramagnetic pulsars experience hyper-violent starquakes, often accompanied by gamma-ray flares. Could their frequent outbursts be extreme versions of the same crust physics driving ordinary pulsar glitches? Evidence points to yes, like in 2020, when magnetar SGR 1935 + 2154 glitched seconds before unleashing a colossal flare. The event supported the crustal plate model, where magnetic stresses and rotational strain reach a breaking point simultaneously. What makes glitches more than just celestial curiosities is what they reveal about neutron star interiors and environments where matter is squeezed beyond nuclear density, yet behaves like both a solid and a frictionless fluid. By studying these microscopic speed bumps, we're probing states of matter that can't be recreated in any lab, decoding how the universe behaves under conditions so extreme they blur the line between astrophysics and quantum mechanics. Every glitch is a postcard from a realm where the familiar rules of physics twist into something wondrous and utterly alien. In the 1840s, astronomers witnessed something impossible, a star in the southern constellation Carina suddenly flaring brighter than the planet Venus, becoming the second brightest star in the night sky. This wasn't just a twinkle, it was Eta Carinae's great eruption, an outburst so violent it ejected more than 10 times the Sun's mass into space. For nearly 2 decades, this stellar behemoth, already one of the most massive stars known, raged like a cosmic supernova, except it didn't die. Instead, it survived its own cataclysm, leaving behind one of the most breathtaking structures in the universe, the Homunculus Nebula. Hubble's razor-sharp images reveal this hourglass-shaped nebula in stunning detail. Twin lobes of gas and dust stretching a light year across, expanding outward at nearly 7 million kilometers per hour. The nebula's intricate textures, ripples, filaments, and knots tell the story of a star tearing itself apart. Spectroscopy shows it's rich in nitrogen and helium, the ashes of nuclear fusion blasted free when Eta Carinae's radiation pressure overpowered its gravity. But the real shock, the eruption's energy didn't come from the star's core like a supernova. Instead, it was a surface explosion, a titanic belch of plasma triggered by instabilities in the star's outer layers. What caused such chaos? The leading theory points to Eta Carinae's bizarre duality. It's not one star, but two. The primary star weighs 90 solar masses and shines with 5 million times the Sun's luminosity, while its smaller companion, 30 solar masses, orbits every 5.5 years. During close passes, their gravitational tides may have destabilized the larger star, triggering violent mass ejections. Supporting this, the homunculus isn't perfectly symmetrical. Its lobes are slightly lopsided, likely sculpted by the companion's gravitational tug. The aftermath is even wilder. Eta Carinae still teeters on the edge of destruction. X-ray telescopes catch periodic flares as the companion star plunges through the primary's dense stellar wind, creating shockwaves hotter than the Sun's core. Infrared observations reveal hidden dust lanes debris from earlier eruptions, while radio maps show colossal outflows stretching light years into space. And lurking at the center, a stellar vampire, the smaller star siphoning material from its unstable partner, perhaps setting the stage for another eruption. Most astonishingly, Eta Carinae could go supernova any millennium now. When it does, it won't just outshine the moon, it might bathe Earth in enough gamma rays to damage our ozone layer. For now, it's a cosmic time bomb, offering a front-row seat to the death throes of a star so massive it defies the laws of physics. Every telescope trained on it captures a snapshot of stellar evolution's most violent chapter, a preview of how the universe's mightiest stars light their own funeral pyres. White dwarfs are the universe's ticking time bomb, stellar embers so dense a teaspoon of their material would weigh as much as an elephant. Yet these silent remnants hold a dark secret. Push them past a critical threshold, and they'll detonate with the fury of a billion suns. This is the fate of a Type Ia supernova, one of the cosmos' most precisely predictable explosions, and a tool so vital astronomers use it to measure the universe itself. The trigger lies in mass. A white dwarf survives by balancing gravity's crush against quantum forces in its core, but only up to 1.4 times the Sun's mass, known as the Chandrasekhar limit. Cross that line, and the star's carbon-oxygen core ignites runaway fusion, burning through its fuel in seconds. The entire dwarf vanishes in a thermonuclear fireball, outshining entire galaxies. No neutron star or black hole remains, just an expanding cloud of iron, silicon, and nickel blasted into space. Kepler's supernova, observed in 1604, offered humanity's first recorded glimpse of this phenomenon. For weeks, it shone brighter than Jupiter, visible even in daylight. Today, telescopes like Chandra reveal its remnants, a ragged sphere of glowing gas 16 light-years wide, rich with the very elements forged in that cataclysm. But Kepler's true legacy lies in what it taught us. Type Ia supernovas aren't just spectacular, they're eerily uniform. Because all white dwarfs explode at the same mass limit, their peak brightness is nearly identical, making them cosmic standard candles. This reliability lets astronomers calculate distances across the universe. By comparing a Type Ia's observed brightness to its known intrinsic brightness, they can pinpoint how far away it is, like judging a lighthouse's distance by how dim its beam appears. In the 1990s, these measurements led to a shocking revelation. The universe isn't just expanding, its expansion is accelerating, driven by a mysterious force we now call dark energy. Without Type Ia supernovas, we might never have uncovered one of cosmology's greatest mysteries. Yet these explosions aren't just measurement tools, they're also cosmic alchemists. The iron in your blood, the calcium in your bones, even the nickel in your coins were likely forged in white dwarf detonations long before our sun ignited. Every Type Ia is a furnace scattering the ingredients for future stars, planets, and life across the void. And though we've mapped thousands, questions linger. What nudges a white dwarf past its limit? Most theories point to binary systems, either two dwarfs merging or one siphoning material from a companion until it catastrophically overflows. Each new discovery peels back another layer, proving that even the universe's most predictable explosions hide untold complexity. Whether serving as cosmic yardsticks or element factories, these stellar fireworks remind us that destruction and creation are two sides of the same coin, and that sometimes the universe's most violent ends light the way for new beginnings. Gamma-ray bursts may flare and fade in the blink of a cosmic eye, but their fingerprints linger long after the initial blast, a multicolored echo of radiation slowly revealing their secrets. Unlike the initial gamma-ray flash that lasts mere seconds, these afterglows can shine for days or even weeks across the electromagnetic spectrum, from high-energy X-rays down to radio waves. It's as if the universe leaves a breadcrumb trail leading straight back to the explosion's origin, if you know how to track it. The real game changer came with NASA's Swift Observatory, a nimble spacecraft designed to pivot like a cosmic owl at a moment's notice. Launched in 2004, Swift carries 3 telescopes working in tandem. The Burst Alert telescope to catch the initial gamma-ray flash, followed instantly by X-ray and ultraviolet optical telescopes to lock onto the fading glow. This rapid response system lets astronomers pinpoint GRB locations within minutes, sometimes even seconds, transforming these fleeting events from mysteries into detailed case studies. Take GRB 050909, spotted by Swift just 77 seconds after its gamma-ray pulse began. Within hours, telescopes worldwide swiveled to study its X-ray afterglow, revealing a shockwave plowing through interstellar gas at 99.9% light speed. As days passed, the glow shifted wavelengths like a cosmic chameleon, first X-rays, then visible light, finally fading into radio static. This color evolution wasn't random. It mapped the explosion's energy dissipating through different layers of debris, offering physicists a play-by-play of the shockwave's behavior. But afterglows do more than just trace explosions, they illuminate entire galactic neighborhoods. The light from GRB afterglows acts like a cosmic backlight, absorbing specific wavelengths as it passes through gas clouds in host galaxies. This absorption fingerprint lets astronomers inventory distant galaxies' chemical compositions without ever resolving them directly. In 2022, the afterglow of GRB 22109 revealed a galaxy so primitive its gas contained almost no heavy elements, a relic from when the universe was barely 800 million years old. Perhaps most astonishing is how these fading embers solve GRB distance puzzles. Short bursts often leave faint, rapidly fading afterglows hinting at neutron star mergers in elderly galaxies, while long bursts produce luminous, lingering glows tied to massive stars in star-forming regions. Without afterglows, we'd have no way to confirm these connections, just fleeting bursts vanishing into the dark. Now, thanks to Swift and its successors, every GRB is a potential Rosetta Stone, its afterglow a luminous key unlocking cosmic history. On October 15, 1991, a cosmic bullet ripped through Earth's atmosphere with energy so staggering it defied belief, striking with the force of a baseball traveling at 60 miles per hour, all packed into a single proton. This was the oh my god particle, a cosmic ray carrying 320 electronvolts of energy, millions of times more powerful than anything produced in human-made particle colliders. To put that in perspective, its energy was equivalent to dropping a brick from waist height at the atomic scale. The discovery sent shockwaves through astrophysics. Nothing in our galaxy could plausibly launch a particle to such extreme speeds. Even supernova shockwaves fall short by orders of magnitude. The particle's trajectory, traced backward by the fly's eye detector in Utah, pointed toward empty intergalactic space. No nearby galaxies, no active black holes, just the cosmic void. This raised an unsettling question. What cosmic accelerator could possibly fling protons with such violence? One theory points to active galactic nuclei supermassive black holes like the one powering Centaurus A, whose relativistic jets might boost particles to extreme energies. Yet even these monsters struggle to explain the oh my god particle's energy without invoking unknown physics. Some models suggest magnetic reconnection events in AGN jets could act like cosmic slingshots, or perhaps the particle was a rare statistical outlier from a distant, hyperactive quasar. Then there's the wild card, exotic phenomena beyond standard astrophysics. Cosmic strings hypothetical spacetime defects left over from the Big Bang could theoretically generate such energies if they snap. Others propose decaying super-heavy dark matter particles, annihilating in bursts of ultra-high-energy debris. The particles' isolation deepens the mystery. Most extreme cosmic rays cluster around known sources, but this one came from nowhere special or just another patch of sky. Decades later, the oh my god particle remains an enigma. Modern detectors like the Pierre Auger Observatory have spotted a handful of similar ultra-high-energy events, yet none quite match its record-breaking punch. Each new detection inches us closer to understanding whether these particles are cosmic accidents or signatures of physics we've yet to imagine. One thing's certain: the universe still holds accelerators powerful enough to humble our wildest theories, and they're firing bullets at us daily, waiting to be decoded. While supernovas steal headlines with their galaxy-shaking finales, their smaller cousins, classical novas, prove that even stellar outbursts come in different sizes. These aren't star-killing explosions, but rather spectacular surface eruptions on white dwarfs, the dense remnants of dead stars. Picture this: a teaspoon of white dwarf material weighs as much as an elephant, packed into a smoldering sphere no larger than Earth. Now imagine such an object locked in a gravitational tango with a normal star, siphoning hydrogen from its companion like a cosmic vampire. Over decades or centuries, that stolen gas piles onto the white dwarf's surface, compressed by unimaginable gravity until, boom, the pressure ignites runaway nuclear fusion. What follows is a thermonuclear firestorm bright enough to outshine entire star clusters for weeks. Recurrent novas like T Pyxides take this cycle to extremes. Unlike one-time classical novas that may only flare once every 100,000 years, repeat offenders like T Pyxides erupt every few decades. Its last outburst in 2011 blasted material outward at nearly 5 million miles per hour. The reason: these systems are ticking time bombs where the white dwarf teeters just below the Chandrasekhar limit, that critical 1.4 solar mass threshold that could trigger a Type Ia supernova. Each eruption peels away some of the accumulated material, but some theorists speculate recurrent novas might eventually cross the line, gradually nudging their white dwarfs toward the ultimate explosion through successive smaller blasts. The differences between novas and supernovas couldn't be starker. Where supernovas obliterate their progenitor stars, novas leave their white dwarfs intact, ready to resume their deadly feast. Supernovas forge elements like silicon and iron in their cores. Novas mainly cook lighter elements like helium and carbon in their surface detonations. Yet both scatter enriched material into space. T Pyxides' ejecta, for instance, contain unexpected amounts of neon and magnesium, elements normally buried deep in stellar interiors. These chemical fingerprints help astronomers trace how the universe recycles matter, proving that even small cosmic explosions play vital roles in galactic evolution. What makes recurrent novas particularly fascinating is their unpredictability. Ares Ophiuchi, another famous repeater, has flared 6 times since 1898, but its intervals range from 9 to 26 years. Each eruption leaves the system changed. Sometimes the companion star swells from the blast's heat, altering how much fuel gets siphoned for the next cycle. Other times, the white dwarf's magnetic field channels the explosion into jets, sculpting the ejected material into intricate shapes visible in Hubble images. It's a cosmic laboratory where we watch stellar physics play out in fast forward, offering clues about how binary stars evolve and when their dance might end in total annihilation. The boundary between just a nova and a full supernova blurs in systems like Scorpii, where eruptions occur so frequently every 10 years or so that astronomers suspect its white dwarf is inching toward catastrophe. If enough hydrogen-rich material survives each blast and sinks to the dwarf's core, the increasing mass could eventually trigger carbon ignition, the runaway reaction that defines a Type Ia supernova. That's the irony of these seemingly smaller explosions. They might be rehearsals for the universe's most precisely calibrated detonations, the same standard candles we use to measure cosmic expansion. Every recurrent nova we study adds another piece to the puzzle, revealing how the universe transforms stolen starlight into both creation and destruction on the grandest scales. At the heart of large galaxy clusters, supermassive black holes don't just devour matter, they shape the destiny of entire galactic neighborhoods in a delicate cosmic balancing act. This phenomenon, called AGN feedback, reveals how the universe's most violent explosions become architects of order, regulating star formation with precision that borders on artistry. The Perseus cluster, a sprawling metropolis of galaxies 190 million light-years away, offers the perfect case study. Chandra X-ray observatory images reveal vast, symmetrical cavities in the cluster's hot gas, each spanning 50,000 light-years, carved by jets erupting from the central galaxy's black hole. But here's the twist: these aren't just scars of destruction. They're coupled with faint, concentric ripples, pressure waves propagating through the cluster like sound waves from a subwoofer, literally playing a note 57 octaves below middle C, the deepest note ever detected in nature. These jets and sound waves form a cosmic thermostat. As gas cools in the cluster's core, it should collapse to form new stars at a voracious rate, yet in many galaxies, star formation mysteriously stalls. The answer lies in the black hole's outbursts. When too much gas accumulates, the AGN awakens, firing jets that heat the surrounding medium. The energy injected isn't raw destruction, it's finely tuned, like a chef adjusting a flame. Too little and runaway star formation would exhaust galactic gas reserves prematurely. Too much and the galaxy would be stripped bare. Instead, the AGN delivers just enough energy to keep the gas simmering hot enough to resist collapsing into stars, but not so hot it escapes the galaxy entirely. The numbers are staggering. A single AGN outburst can release enough energy to power a galaxy for millions of years, equivalent to 1 billion supernovas. Yet what's remarkable isn't the raw power, but the precision. In the Perseus cluster, the sound waves carry energy outward with minimal turbulence, gently redistributing heat rather than shredding the gas. Computer simulations show this feedback loop self-regulates like a valve. As gas cools and flows toward the black hole, it fuels new outbursts which then reheat the gas, creating a stable cycle that can persist for billions of years. This balancing act solves one of astrophysics' great puzzles: why massive galaxies aren't even larger. Without AGN feedback, theoretical models produce galaxies 10 times more massive than what we observe, glowing with far more stars than exist. Instead, the black hole's intermittent outbursts act as a cosmic brake, ensuring galaxies grow, but not too fast, not too big. It's a dance of chaos and control, where the universe's most destructive forces become the caretakers of cosmic structure, proving that even in the void, there's a delicate balance between creation and destruction. The Vela pulsar should be predictable, a textbook example of a neutron star spinning with clockwork precision. Its radio pulses arriving every 89 milliseconds like a cosmic metronome. Yet every few years, this seemingly ordinary pulsar shatters expectations by erupting in gamma ray, flares so violent they momentarily outshine the entire Milky Way. These outbursts last mere seconds, but their energy defies explanation, emitting more power in that blink than our sun does in years. What makes these flares so baffling isn't just their intensity, it's that they come from a pulsar with no business producing them. Pulsars like Vela are supposed to be stable. Born from supernova explosions, their emissions stem from precise beams of radiation powered by rapid rotation and strong magnetic fields. But Vela's gamma-ray tantrums suggest something far more chaotic lurking beneath its surface. In 2016, NASA, a Fermi Gamma-Ray Space Telescope, caught one such flare in action, a spike of high-energy photons 100 times brighter than the pulsar's usual output. The event contradicted every model of pulsar magnetospheres, which predicted smooth, steady particle acceleration, not violent, sporadic bursts, the leading theory. Starquakes meet magnetic reconnection. Deep beneath Vela's iron crust, enormous stresses build as the neutron star gradually slows its spin. When the crust fractures, suddenly shifting even a millimeter, it unleashes a seismic shockwave powerful enough to reconfigure the pulsar's magnetic field lines. Like rubber bands snapping, these lines violently reconnect, accelerating particles to near light speed in a process usually seen on the Sun, but scaled up to ludicrous extremes. The result is a gamma-ray firestorm, particles colliding so fiercely they spawn antimatter pairs in their wake. But here's the twist: Vela's gamma-ray flares don't always align with its radio pulses. Some erupt between rotations, implying the explosions originate far above the surface, perhaps in the pulsar's outer magnetosphere where magnetic fields twist into knots. This challenges the classic lighthouse model of pulsars, suggesting their magnetospheres are far more turbulent and dynamic than we thought. Even stranger, Vela's flares seem to remember past outbursts. Statistical analyses reveal clusters of activity, as if the pulsar cycles between calm and stormy periods. The implications stretch beyond Vela. If a well-behaved pulsar can suddenly turn ferocious, what does that mean for magnetars, neutron stars already infamous for their violent outbursts? Could all pulsars harbor this hidden fury, lying dormant for centuries before unleashing their wrath? Each flare peels back another layer of mystery, proving that even the cosmos' most predictable timekeepers keep a few explosive secrets up their sleeves. While the universe's most energetic explosions unfold across unimaginable distances, Earth has hosted its own apocalyptic detonations, none more devastating than the asteroid impact that erased the dinosaurs. 66 million years ago, a chunk of space rock the size of Mount Everest slammed into what's now Mexico's Yucatan Peninsula, releasing energy equivalent to 100 teratons of TNT. To put that in perspective, it's 10 billion times more powerful than the Hiroshima bomb, a flash of destruction that bridges the gap between terrestrial catastrophes and the cosmic violence we've explored. The moment of impact was pure astrophysics incarnate. Traveling at 45,000 miles per hour, the asteroid compressed air and rock into plasma hotter than the Sun's surface, vaporizing itself and 100 cubic miles of Earth's crust in microseconds. The explosion carved a crater 110 miles wide, blasting debris so high it breached the atmosphere, some even reaching escape velocity, destined to drift forever among the stars. But the real horror came afterward. Superheated ejecta rained back globally, igniting continent-spanning wildfires as temperatures briefly soared to oven-like extremes. Then came the nuclear winter. Sunlight-blocking aerosols from vaporized sulfur-rich rock plunged the planet into darkness for years, collapsing food chains from the bottom up. Acid rain poisoned oceans, while shockwaves triggered earthquakes and tsunamis that reshaped coastlines thousands of miles away. Here's where cosmic and terrestrial explosions intersect. Like a gamma-ray burst sterilizing nearby galaxies, Chicxulub's aftermath wasn't just localized destruction, it was a systemic reset. The event's energy distribution mirrors astrophysical blasts, immediate thermal radiation, think supernova flash, followed by kinetic shockwaves akin to hypernova debris, and finally, long-term atmospheric perturbations resembling AGN feedback on galactic gas. Even the crater's peak ring, a circular mountain range within the impact basin, has lunar and Martian counterparts, proof that the physics of high-energy collisions transcends planets. Yet Chicxulub also stands apart. Unlike cosmic explosions that forge elements, this one selectively preserved life's ingredients. Fossil records show small, adaptable species, early mammals and birds, surviving where giants perished, their descendants inheriting a planet stripped of competitors. Ironically, the same impact that annihilated 75% of species also cleared ecological niches for our ancestors, setting the stage for humans to eventually ponder such cataclysms. Modern astronomy sharpens the connection. The asteroid likely originated from the inner solar system's debris, remnants of the same chaotic processes that birth comets and meteors. Today, programs like NASA DART mission test deflection strategies, proving we've begun viewing Earth as part of a dynamic cosmic shooting gallery. Chicxulub wasn't just a disaster, it was a cosmic reminder that even on our pale blue dot, the universe's explosive fury is never truly distant. The future of cosmic explosion research isn't just about refining what we know. It's about discovering phenomena we can't even imagine yet. Groundbreaking observatories now under construction promise to peel back the universe's most violent secrets with unprecedented clarity. Picture the Cherenkov Telescope Array, or CTA, a next-generation gamma-ray observatory spanning 2 hemispheres with over 100 ultra-sensitive telescopes. Unlike current instruments that merely detect gamma rays, the CTA will map them in exquisite detail, tracing particle acceleration in supernova remnants, probing the chaotic hearts of active galaxies, and perhaps finally solving the enigma of fast radio bursts. Its precision could reveal whether FRBs are truly magnetar tantrums, or something far stranger like cosmic strings vibrating through space-time. Then there's LISA, the Laser Interferometer Space Antenna, a trio of satellites set to form a 1,000,000-kilometer-wide gravitational wave detector in orbit. Where LIGO catches the final seconds of black hole mergers, LISA will sense the hours or even days leading up to collisions, like hearing the deep hum of neutron stars spiraling toward each other long before their explosive finale. This could unveil entirely new classes of events, intermediate mass black holes tearing apart stars in slow motion, or the primordial ripples from cosmic superstrings predicted by string theory. LISA might even catch the gravitational echoes of hypernovas, whose asymmetrical collapses could leave space-time ringing like a bell. But the revolution isn't limited to big-ticket projects. Vera Rubin Observatory's upcoming Legacy Survey of Space and Time will scan the entire southern sky every few nights, catching supernovas hours after ignition, something never before possible at this scale. Imagine pinpointing a star's death throes so early we witness the shockwave breaking through its surface, or catching the birth flare of a magnetar in real time. Meanwhile, the square-kilometer array, with its thousands of radio antennas, will dissect fast radio bursts with millisecond precision, potentially decoding their origins by tracking how their signals twist through intergalactic magnetic fields. The most exciting prospect, these tools won't just answer existing questions, they'll expose gaps in our understanding. Every time humanity has built a more sensitive observatory, we've stumbled upon entirely new cosmic phenomena: pulsars, gamma-ray bursts, gravitational waves. The next decade's discoveries could rewrite textbooks, whether it's spotting dark matter particles annihilating in dwarf galaxies or capturing the birth cry of a black hole in a laboratory of pure gravity. One thing's certain, the universe's most spectacular fireworks are far from fully catalogued, and the best seats in the house are still being built. From gamma-ray bursts that outshine galaxies to kilonovas forging gold in cosmic collisions, we've journeyed through 30 of the universe's most unimaginable explosions, events so powerful they redefine the limits of energy itself. Picture the sheer scale. A single hypernova unleashing more energy in seconds than our sun will emit in its entire lifetime, or a magnetar starquake cracking its crust with the force of a magnitude 23 earthquake. Now imagine the Vela pulsar's gamma-ray flare's brief tantrums brighter than the Milky Way, or the Chicxulub impact, an asteroid strike that reshaped Earth's destiny with the violence of a terrestrial supernova. These aren't just distant curiosities, they're the engines that forge the elements in your body, the forces that sculpt galaxies, and the echoes of chaos that birthed order in the cosmos. Yet for all their fury, these explosions reveal a humbling truth. Humanity exists on the faintest edge of cosmic time and space. The gold in your jewelry was stamped into existence by colliding neutron stars billions of years before Earth formed. The oxygen you breathe was blasted into space by dying stars long gone. Even the atoms in your hands carry scars from the Big Bang's unfathomable heat. We are, in every sense, stardust shaped by the universe's most violent moments, a fleeting whisper against the roar of cosmic detonations spanning eons. So here's the challenge. Which fact left you breathless? Was it the Fermi bubbles towering over the Milky Way, proof of our black hole's explosive past? Or perhaps the oh my god particle, a single proton packing the punch of a fastball? Whatever it is, let's keep the conversation exploding. Drop your thoughts below. Share this cosmic fireworks show with a friend. And remember, every time you look up at the night sky, you're glimpsing the aftermath of the universe's greatest spectacles. The cosmos isn't just out there, it's in you, and the story is still being written.